So our task today is to continue using the derivative to find out stuff about functions. And in particular today we're going to look at increasing, decreasing, and again at these relative extrema. So think way back to early in the semester where we were given graphs, pictures of these gondola rides. And what we had to do is we had to figure out where they were increasing and decreasing. And so visually it's not too hard to see that we're increasing here along this sort of stretch and we're decreasing here. And in between them we have this relative maximum. Now, it's not so bad to do it graphically, but what we want to do is we want a way to do it without having to graph it all the time, and also to do it very precisely. So looking at this graph, it looks like somewhere around here, around 135 seconds, we switch from increasing to decreasing, but what we want to do is we want to figure this out very precisely instead. So to be precise, what we want to say is a function f is going to be increasing on an interval if for any two numbers x1 and x2 in the interval, if x1 is less than x2, then f of x1 is less than f of x2. So what we can draw on our graph here is we have an x1, we have an x2, x1 is less than x2, it's to the left of it, and if we look on our graph and we look at how high our output is, we have f of x1, we have f of x2, and we can see that f of x1 is sort of below f of x2. So we're moving on up. Decreasing is very similar. We're still going to move from the left to the right. So here's a different x1, a different x2, but now f of x1 is going to be higher than f of x2. So it's the same basic idea, it's just switched, where instead of going up, we're going down. So our first tool we're going to use in this section is called the test for increasing and decreasing functions, which says if you have yourself a function that's continuous, no breaks, differentiable, no corners, then if the derivative is positive on that interval, then f is going to be increasing. We can also see it says if the derivative is negative, it's going to be decreasing, and if the derivative is 0, then it's going to be constant. So the thing to remember is this is visually, it's not too bad to see what's going on here. So if you have yourself part of a graph, and you have yourself at A and B, and what we've got is for everywhere in between here, we're saying the derivative is positive. So if I just go up here, I'm going to say, well, my derivative is positive, which means I can get this upward looking slope. I got this upward looking slope, I got an upward looking slope. Well, that means that my graph, since these are my slopes, my graph has to sort of be moving in an increasing direction. Similarly, for part 2, if I've got myself some negative slopes, so remember that negative slopes overall kind of have this downward looking thing. That means your function is decreasing. And finally in step 3, or part 3 rather, it says that, well, if your slope is always 0, well then you can't help, you're not moving up or down. Slope really tells you, is your function moving up? If it's positive, your function is moving down if it's decreasing, and it's not moving at all if it's 0. Now what's really neat also about the test for increasing and decreasing functions is it really lists out the 4 possibilities for derivatives. The first possibility is that your derivative at a point is positive, your derivative could also be negative, your derivative can equal 0, and the last possibility that of course is not in the theorem is that your derivative does not exist. So this is all that can happen. It's positive, you're going up, it's negative, you're going down, it's 0, which means you're constant, or it does not exist, which means you have a critical point. So what the previous theorem, test for increasing and decreasing, really helps us figure out is it helps us figure out increasing or decreasing parts of functions, and it tells us that we actually don't need to look at the function at all, we just need to look at the function's derivative. So here what we're going to do is we're going to figure out where a function is increasing, decreasing, or constant by only looking at its derivative. We don't even know what the original function is, but I know it has derivative 3x squared minus 12x. So the first thing you want to do when you want to figure out where our function is increasing, decreasing, or constant is to first look at places where we get critical numbers of our function. So recall that critical numbers are going to be places where either the derivative does not exist or where the derivative is equal to 0, right? To find increasing and decreasing, we need to know where the function is positive or negative. So one way to do that is to first figure out where it's not positive or negative, that is where it does not exist, or where it's equal to 0. In this case, we don't have any places where our derivative does not exist. It's a nice looking derivative. But if we set our derivative equal to 0, what we can do is we can work through the algebra factor and solve this a little bit, and we'll get that at x equals 0 and at x equals 4, we have ourselves critical numbers. And what these critical numbers do is I can take a number line here, and I can mark them on my number line, and I know that my derivative is going to be 0 at these places. So what I can do is I can write down here, well, what happens to my derivative? Well, at 0 it's 0, and at 4 it's 0. And now what I want to do is I really want to figure out what happens in between these numbers. And I know it can't be 0 or does not exist, because I've already found those places as critical numbers. So instead what it's going to be is it's either going to be positive or negative for the entire stretch. Whatever it is between 0 and 4, if it's positive or negative, it's going to be positive or negative the entire time. And so what that means is I'm going to have these test intervals. That is, my test intervals are going to be negative infinity up to 0, 0 to 4, and finally 4 to infinity. I need to figure out if I'm increasing or decreasing on these intervals, because it has to do one or the other. So now what I need to do is I need to look at my intervals, and I'm going to choose 1 point on each of the intervals. And it doesn't matter which point I pick, I just pick one that's convenient. So what you need to do is you need to think, well, what's your favorite number between negative infinity and 0? My favorite number happens to be negative 1. What's your favorite number between 0 and 4? My favorite number happens to be 1. And finally, between 4 and infinity, I'm going to go with 5. These are nice numbers. You get to choose them. You may as well choose nice numbers. And now what you want to do is you want to test them in the derivative. Okay? Because if you put this number in, and depending on if it's positive or negative, that tells you what your function's doing. So we perform our test in f prime of x. So now I take f prime of negative 1. I run through my arithmetic, and I find out that this is going to be 15, so that's a positive number. I test 1 in my derivative. I run through my arithmetic, and I think if I do everything correctly, I end up with a negative 9, overall a negative number. And finally, I test 5 in my interval. I run through my arithmetic, and I end up with, if everything went well, I'm going to get 135, but overall a positive number. So going back and thinking back to my test for increasing and decreasing, what this tells me is this tells me that I'm increasing, decreasing, and finally increasing. So now I can just wrap this up in a nice sentence. So I can say the function f of x, the original function, is increasing on the intervals negative infinity to 0 and 4 to infinity, and decreasing on the interval from 0 to 4 from this test. So everything is going to be done the same. First, what you do is you find the critical numbers. So in this case, we had critical points at 0 and 4. We look at the intervals, we test the numbers on there, and then we conclude on those intervals what our function is doing overall. No messing about by looking really closely at a graph. It's just a couple simple tests to figure out what our function is doing. So before we talk about the next big idea in the section, we have our keyword for the day. It's Packers, the greatest football team ever to exist. So make sure you answer that in your quiz. But now, what we want to do is we want to look at the first derivative test. So think back to when we looked at our roller coasters. It was pretty easy again to estimate where the top of a roller coaster was or where the bottom was. But again, we don't want to estimate, we want to know these exactly. So the first derivative test will tell us exactly where these places are. So the first derivative test says we need to do a couple things. First, we need to make sure we have c, a critical number of a function, and that it's continuous there. It's actually going to be defined at this point, c, so it's a solid dot. We also need to be differentiable around c, maybe not at c, maybe it's not differentiable there, but we can at least find the derivative around it. And what our first derivative test says is it says that if our derivative changes from negative to positive, it has to be a relative minimum. So let's think about what this says. Part 1 says we're going along. We have this point C here. It's at least defined in our function because it's continuous through there. It might not be differentiable, but what we've got is we've got our derivative changing from negative to positive. So that means in our function, we're coming down here. We've got a negative derivative. We change to a positive derivative. Well, what does that mean? That really does look like a relative minimum here of our function. Well, let's look at what part 2 of this theorem says. So again, we start with the same basic setup. We've got this point C here on our function, but now we're changing from a positive derivative to a negative derivative. Well, that certainly does look like a relative maximum of our function. And finally, what does 3 say? 3 says that if it's positive or negative on both sides, that way it means it doesn't change, it's going to be neither a maximum nor a minimum. So let's draw a picture of what this looks like. So this says that, if you're coming along, you're positive over here, you're a critical point now, so maybe, the derivative is 0 or it's a corner, and then you keep being a positive number. Well, that's not a relative minimum or a maximum. That means our function just sort of leveled off for a little bit and kept going. So it didn't really hit a max, didn't hit a min, just sort of leveled off. And what's nice now is this theorem gives us a way, without looking at the graph, to really precisely determine where the tops and bottoms of our roller coaster are, if you will, or the maximums and minimums of our function are. So now let's go ahead and make use of the first derivative test to identify all relative extrema and intervals of increase or decrease for a function f of x, which we don't actually know, but we have here its derivative. So the key is we're identifying the relative extrema and intervals for this function f of x, even though we only know its derivative. So the process we go through is exactly the same as first finding the intervals of increase or decrease. The first thing we need to do is we need to find all critical points. So in this case, again, what we want to do is we want to say, well, where is our function, its derivative, equal to 0? Or where does f prime, the derivative, not exist? Well, in this case, we can skip the does not exist because this is going to be a fine function, but what we can do is we can solve and we can say, let's see, 48 is equal to 3x squared, 16 is equal to x squared, so x is going to be plus or minus 4. So these are our possible places to look at. These are our critical points for our function. And what we're going to do with these is we're going to use them on a number line to set up our test intervals. So we need to test between negative infinity and negative 4, negative 4 to 4, and also what we want to look at is from 4 to infinity. So now our same step 2 as before. We test at least one point on each interval for the sign of the derivative. So remember, our intervals that we had were negative infinity to negative 4, negative 4 to 4, and 4 to infinity. And so we have to decide what we're going to test. Well, I'm just going to choose negative 5, 0, and 5, and we test them in the derivative. So we take the derivative at our test point. So if I put negative 5 into my derivative, I actually can't remember what number I get, but it's positive. If I put 0 into my derivative, it looks like it's going to be negative. And finally, if I put 5 into my derivative again, it's going to be positive. So overall I went positive, negative, positive. So thinking back, what this tells me is this tells me decreasing, increasing, and finally decreasing again. And so this tells me about my intervals, right? I've got my intervals figured out. But I also wanted to figure out what happens to my extrema. Well, let's think through. So if my function here, it goes from decreasing to increasing at negative 4, that's a relative minimum. So I have myself a relative min at negative 4 and whatever you would get if you put negative 4 into the original function. And over here I'm going from increasing to decreasing at 4. So this means I have myself a relative max at 4 f of 4. So it's the same basic process as finding out what's happening on the intervals, except we just go one step further and use that information to conclude something about our original function, that we have relative mins and relative maxes. So let's go ahead and try one more example, but with a much more interesting function. In this case, again, I don't know what my original function g of x is, but it doesn't matter. But I have its derivative here that I can work with and figure stuff out about. So as always, step 1, I need to find my critical points, my critical numbers. So in this case, I set my derivative equal to 0. So I've got 4 over x times 3 times x squared minus 4 to the 1/3. Now I'm only going to get 0 when the numerator is 0, so really what I can get away with is just figuring out where 0 equals 4x. So in this case, I get x equals 0. And this is a number that makes my derivative equal to 0. I also need to figure out where my derivative does not exist. And these places, of course, we always look and think, well, where is this going to make us divide by 0? So we want to solve this equation instead. And after a little simplifying, algebraic maneuvering, we get down that what really matters is x squared minus 4 equals 0, which really means x is going to be equal to plus or minus 2. So now along my number line I've got 3 interesting points, negative 2, 0, and 2. And the thing to remember is that in this case, negative 2 and 2 are actually places where the derivative does not exist. So I will actually tell you what our original function is, because it will matter here in a second. But what we've got from the previously is we've got our intervals set up now at least. So we know what our intervals are that we want to look at. We want to look at negative infinity to negative 2. We want to look at negative 2 to 0. We want to look from 0 to 2. And we also want to look from 2 to infinity. So now we need to pick some test points. Again, test points, you just pick whatever numbers sound good to you. The numbers that sound good to me are negative 3, negative 1, 1, and 3. And now we test them in our derivative. So we take g prime of negative 3. We run through the arithmetic on this thing. And overall, we're going to end up with a negative number. We run through the arithmetic on putting negative 1 in the derivative. We end up with a positive number. We run through the arithmetic of putting 1 in, and we also get a negative number. And finally, when we put 3 into this derivative, we end up with a positive number. So we went negative, positive, negative, positive. So this tells me decreasing, increasing, decreasing, and increasing. And the last thing we want to do is now we want to figure out, well, what about our relative extrema? Well, we want to think, well, what happens here at negative 2 g of negative 2? Well, here, since this is actually a number, and what happens is according to this function, we will go from decreasing to increasing. So our function goes decreasing, increasing. What we've got here is we've got a relative minimum. By similar arguments, what we can see is we can see that at 2 g of 2, we also are going to go decreasing, increasing, so we have a relative minimum. And finally at 0 g of 0, well, in this case we went the other way. We went from increasing to decreasing, so we have ourselves a relative max. But all of these are going to be solved in very similar ways. We find the critical points, which allow us to break up into intervals. We test our intervals to see if they're increasing or decreasing, and from these we can conclude where we have minimums, where we have maximums, and where maybe we have nothing happening. As always, try the problems posted, take the quiz, and we'll talk more about this in class. Thank you.